Dr. Rizwana, working as Professor of Physics in Institute of Aeronautical Engineering. Today we are going to discuss some definitions and terms related to lasers and fiber optics. So this will help us to understand these lasers and fiber optics more in detail. And already in my previous videos, I have discussed about what is a laser, what are the different phenomena that are there in order to get laser emission, and also we have seen uh, what is the block diagram of a laser system, and also we have discussed different types of lasers along with their applications. And coming to fiber optics, we have discussed about the construction principle, and of course very important terms related to fiber optics like acceptance angle, acceptance cone, and numerical aperture. And apart from that, we have discussed different types of optical fibers. That classification we have discussed based on number of modes of propagation and refractive index profile, as well as what type of material it is used in order to make optical fibers. And in the end, we have taken block diagram of optical fiber communication system. So now, taking into consideration all those topics, we are going to discuss some definitions. As I told you that they are going to help us to understand them better. So moving further, coming to first definition here, define laser. So what do you mean by define laser? What is the full form of laser? Laser stands for light amplification by stimulated emission of radiation. And then next, explain the phenomena of absorption. So what is absorption? We know that if we take a system of atoms and if we have two active energy levels which are denoted as E1 and E2, first atom, it will be there in ground state, and when we expose this particular atom or electron to a photon whose energy is equal to E2 minus E1, then this atom or electron absorbs that energy and it goes to higher state. And this phenomena it is called as absorption. Then coming to spontaneous emission. What is spontaneous emission? After absorption, atom it will be there in the excited state, and then what you will observe here is for how long it will stay in that excited state for its lifetime. After lifetime, what happens to this atom? This atom it will de-excite to ground state, and when it de-excites it will emit a photon. And we know that due to spontaneous emission, whatever photons are emitted, they are out of phase with each other, and what type of radiation will get because of this spontaneous emission will get incoherent, as well as polychromatic and also less intense radiation. Then what is stimulated emission? So stimulated emission, very important phenomena required for laser emission, and in this case here also, after absorption, atom it is there in the excited state. Now we have to make this atom come down before its lifetime. So for that, we are doing, we are making a photon to incident on this atom. Then this atom, when it comes down, when it gets de-excited with the help of this stimulus energy, then two photons are emitted per emission. And whatever photons are emitted due to stimulated emission, they are of same wavelength, they will be traveling in single direction, and they are in phase with each other. And of course, highly intense beams. So ultimately, we are going to get laser light because of stimulated emission. Now, coming to fifth definition, what are the characteristics of a laser? When we are discussing about characteristic of a laser, there are four characteristics. One is directionality, coherence, monochromicity, and highly intense. Then what are Einstein coefficients? So Einstein coefficients, these are the mathematical quantities that will measure probability. Probability means rate at which the phenomena is taking place per unit time. So probability of absorption or emission of light, and in this emission we are going to discuss both about spontaneous and stimulated emission. So those mathematical quantities which measure such probability of these phenomena, those are called as Einstein coefficients. Then define metastable state. Already we know that each energy state it will have its own lifetime, and when we go for excited state, there will be one excited state whose lifetime will be longer. Such state it is called as metastable state. Then what is population inversion? So coming to population inversion, we know that generally if we take lower state and higher state, And if lower state population is N1 and higher state population is N2, we know that generally under normal condition, when we are not supplying any energy, population of N1 state will be greater than N2. But if we supply energy to these atoms, when they go up, then we'll observe that population of higher state will become greater than lower state. Such situation it is called as population inversion. And describe pumping. What is pumping? We know that in order to achieve population inversion, what we have to do, we need to supply energy. So this process of supplying energy in order to achieve population inversion is nothing but pumping. And then coming to 10th definition, explain optical resonator in a laser system. So what is optical resonator? Now we know that if we take any laser system, it consists of three main parts. What are those three main parts? We have active medium. So it is the medium in which we have metastable state, and it can be a solid, liquid or gas. And then we have source of energy. So we have energy being supplied by source. And then on either side of the optical medium, we have two mirrors. So of these two mirrors, one is perfect reflector and other one is partial reflector. So what is the role of these mirrors? Once we get photons, these photons, they'll undergo back and forth reflection at these mirrors, and they'll act as stimulus energy to get stimulated emission. And because of the stimulated emission, lasing action will start and we'll get plenty of photons, which gives rise to laser light. The next one, what do you remember by active medium? As I told you, active medium, it can be in any form, okay, which consists of atoms, molecules or particles or electrons. And here it has got a metastable state. What is metastable state? Higher state which has got long lifetime. And what happens in metastable state? Population inversion will be achieved. And because of de-excitation of atoms in metastable state, we are going to, by stimulated emission, we are going to get our laser light. What are direct bandgap semiconductors? So in direct bandgap semiconductor, if you consider two active energy levels, suppose one is E1, other one is E2, and if we consider difference between these two states, which is E2 minus E1, it is equal to H nu, which is equal to energy of photon. So when atom de-excites from higher state to lower state, it is going to emit energy in the form of light. And here, how we'll form these direct bandgap semiconductors? By combining different elements of different groups. And if you can take example, gallium arsenide, indium phosphide, etc. Then define fiber optics. What is fiber optics? Of course, fiber optics, it is related to optical fiber, where we talk about transmission of information through a guiding channel, which is nothing but fiber material and with negligible loss. And what is the principle of working of optical fiber? So if we take optical fiber, we know that optical fiber, it consists of core and cladding, and in our information, it will be transmitted only inside the core. And once your light ray enters this core, and when it goes and strikes core cladding interface, it will undergo total internal reflection. It means that it travels only inside the core medium. That is the principle of working of optical fiber. Then recall critical angle. So if you are given a optical fiber where core refractive index, if it is given by N1 and cladding refractive index is given as N2, how will define this critical angle? This critical angle, it is given as sine inverse of ratio of refractive index of cladding to the refractive index of the core. Or what you will observe here is, when we make our light incident on core cladding interface at internal incidence angle equal to theta c, then our light ray, it moves along the interface. And in order to go for total internal reflection, we have to maintain our internal incidence angle at core cladding interface to be greater than critical angle. Then next, what is acceptance angle? So here, what is acceptance angles? What we do when we launch our light. So when we are launching our light inside the core medium, suppose this is core and this one is cladding. And when we are, suppose this is our fiber axis, and when we are launching light, we are launching at one particular angle of incidence. That angle, it is called as alpha maximum, for which light ray enters core, and when it strikes core cladding interface, what is the internal incidence angle? It is equal to theta c. And what we have to do always, we have to launch our light at angles less than this maximum angle of incidence, so that here angle it should be greater than theta c, then only total internal reflection takes place. So what is our acceptance angle? It is the maximum angle of incidence for which light ray enters core and it strikes the core cladding interface at angle equal to critical angle, so that light ray moves along the interface. So in order to have total internal reflection, our launching angle it should be less than this maximum angle of incidence called acceptance angle. Then what is numerical aperture? It is called light gathering capacity, and numerically it is taken as sine of acceptance angle. And moving further, what are step index fibers? We know that based on refractive index profile of the cone medium, we have two types of fibers. One is step index and one is gradient index. In step index fibers, suppose this is our core and if this is our cladding, and if we consider refractive index profile of core, so what do you mean by refractive index profile of core? Suppose if I am considering, so if I take this figure and here on x-axis I am considering r. R is distance from the center of the core. R is distance from the center of core. On then y-axis I am taking refractive index profile. This is our core medium, and whereas this is our cladding medium, and this one is core cladding interface. So what you will observe here is, in case of step index fiber, refractive index of the core, it is going to be uniform. So when we move from the center of the core, refractive index will be same. And what is the value of that refractive index? It is equal to N1. And when it comes to core cladding interface, it suffers sudden drop in refractive index. And what is the value of that sudden drop? This value it is equal to N2. And as you can make out that this profile, it is in the form of step. That's why these are called as step index fibers. And then what is acceptance cone? Just now we have taken what is acceptance angle. Then what we'll do, inside the optical fiber, we know what is acceptance angle. Once we know acceptance angle, what is the formula for acceptance angle? Acceptance angle formula, it is given as sine inverse of square root of N1 square minus N2 square by N0, where N1 is refractive index of core, N2 is refractive index of cladding, and N0 is refractive index of launch medium. And once we know these refractive index values, once we find this acceptance angle, then what we'll do, we'll rotate this acceptance angle about the fiber axis. Then there will be formation of one cone, okay, whose half angle is acceptance angle, which is alpha I maximum, and this particular cone which is formed by rotating acceptance angle about fiber axis, it is called as acceptance cone. And what is the significance of this acceptance cone? We have to launch our light only within this cone, then only all those light rays will enter core and they'll strike core cladding interface at angles equal to greater than critical angle, and they'll suffer total internal reflection and reach the other end of optical fiber. Then moving further, explain the meaning of graded index fibers. So if you consider here, coming to graded index fibers, again when we are going to consider refractive index profile, so in this case we have seen in step index fiber that when we are taking distance on the x-axis, that is nothing but distance from the center of the core, and of course refractive index. Here in this case, what we'll observe here is, when we go through this core, at the center of the core, refractive index will be maximum, and when we are, as you can see in this figure, so at the center of core, refractive index is maximum, and when we are slowly moving away from the center of the core, refractive index will slowly decrease. And once it comes to cladding, then what happens to, see here in step index fibers, there was abrupt decrease in the refractive index of core when it reaches core cladding interface. But in this case, slowly from the center of the core, refractive index, it is going to decrease, and gradually when it comes to core cladding interface, it will become equal to refractive index of the cladding. Here, refractive index, it is changing in parabolic manner, and such case it is called as graded index fibers. The next, in stimulated absorption, What is the lifetime of atoms? Ground state. So what you will observe here is at the ground state, atoms are perfectly stable unless and until we don't supply any energy, they are going to stay in the ground state. Now what you will observe here is, suppose if we apply force, then they become unstable. All the forces are balanced, then as the atom is stable in ground state, its lifetime is infinity. So here lifetime, suppose if we are not supplying any external energy, any stimulus energy, then atoms, they'll try to stay in the ground state. So that's why we'll say that lifetime of ground state is infinity. Then what are phonons? We know about photons. Photons are energy packets. So these are discrete energy packets that are related to light radiation. But what are phonons? Phonons are also discrete packets of energy. But these decrease here in this case, they are called as quanta of sound waves. So when energy is provided, what you will observe here is lattice absorbs that energy and it gets excited to higher state where we have thermal agitation of atoms, and when it de-excites to ground state, it releases in the form of sound wave energy, and that energy it is called as phonon. The next, laser, it is used in lidar for what purpose? Now if we take lidar, what is the full form of lidar? Light detection and ranging. And laser, it is used in lidar for what purpose? For range finder. So what you will observe here is the transit time of transmitted and reflected pulse of laser light is recorded and distance of reflecting object is estimated. Then where is neodymium YAG most commonly used? So this neodymium YAG laser, it is used for cosmetic surgeries because it has a property of maximum energy absorption by target. And what is the target? Hair. And here with the minimum absorption by the surrounding skin structure. So mostly it is used in cosmetic surgeries. And then which characteristic of laser it is used in holography? So we know what is holography, where we get three-dimensional image of an object. So production of an image in a hologram takes place via process called as reconstruction. And in reconstruction, what is the property used? Highly coherent property of laser is used. What is the region enclosed by optical cavity called? So optical cavity, it is just like an oscillator as it provides feedback of the photons by reflection in the mirrors. So area enclosed inside the optical cavity is called as optical resonator. Then next, why we need population inversion? We know that we get laser light only because of stimulated emission. And what is stimulated emission? Stimulated emission is forceful emission or de-excitation of atoms from higher state to lower state. So only if we are able to achieve more number of atoms in metastable state, then only we can make them de-excited by stimulated emission. So that's why we need population inversion. So here light amplification takes place by stimulated emission. Now why laser is called as a non-material knife? Because it is used in surgeries. And if you consider laser surgery here, without using any knife and without any loss of blood, actually it is called as bloodless operation. We cut tissues and hence that's why it is called as non-material knife. What is the role of laser in DVD? Now we know that we have DVD player. Okay, so in DVD player, what we'll do, by moving the lens longitudinally, different depths can be reached in the disc, and in order to make room for a lot of information on every disc, then the laser beam has to be focused on a small area, as small as possible, and this cannot be done with any light source. For this we need our laser source. So in order to get different depths on a disc, that's why we make use of laser light. Now why laser is used in vibrational analysis of structure? Here if you want to test a structure, okay, when a structure is under test, then what you will observe here is when we expose it to laser, then under vibrational analysis, our structure, it is going to vibrate and a distinct pattern will be emerging, and by analyzing that distinct pattern, we will be able to understand that particular structure better. What is meant by attenuation? Even though we are taking care of so many things in for fiber optic communication, still we'll observe that very small amount of loss of energy takes place. And how to find that loss of energy? That attenuation, it is taken in terms of decibel. Unit is decibel, and how it is measured? It is measured as a ratio of, it's a logarithmic unit where we take ratio of output power to the input power. That is nothing but attenuation. Attenuation is loss associated during propagation of information through optical fibers. Now, what are the losses that occur during optical fiber communication? So, when we talk about those losses, so of course they are called attenuation losses, then distortion losses, as well as dispersion losses. Then state the application of optical fibers in medical field. So, what are the different applications that are used in endoscopy? For medical diagnosis, and also they are used to, so using this endoscopy we can visualize inner organs of the body. We can have direct view of different organs of the body. And also when we talk about these endoscopes, they are used for cardioscopy, laparoscopy, as well as cryoscopy. The next, mention any two fiber optic sources. So whenever we are making use of optical fiber communication, what type of light source we'll use? Either we'll make use of light emitting diode or we'll make use of laser diode. Then what are the conditions for total internal reflection? In order to achieve total internal reflection at the core cladding interface, then what we have to do, first condition is we have to maintain refractive index of core slightly greater than cladding. And second thing is angle of incidence. So when we go here, this angle of incidence at core cladding interface, it should be greater than critical angle. And what is critical angle? It is sine inverse of ratio of refractive index of cladding to the refractive index of the core. Then mention any two advantages of optical fiber communication over radio wave communication. So there are many advantages, but of that when we want to discuss two main advantages, one is they are not affected by any electrical signals or lightning. Why? Because our information, it is in optical form. And second thing is they are free from electromagnetic interference. So that's why we are not going to get any like crosstalk generation or noise generation when we go for optical fiber communication. Then next, in single mode fibers, which is the most beneficial index profile? We have seen that when we take step index profile, so if we take the step index fibers, now different light rays, when we take multi-mode step index fibers, okay, so here in this case, when different light rays take different paths to reach output, then they may not reach output at the same time. So they will take different times to reach output. This particular problem, it is called as dispersion. But this problem of dispersion, we are able to overcome in graded index fibers. In graded index fibers, when we take fiber axis, so propagation, it will be in helical manner. And here refractive index profile of core is not uniform. And what we'll observe here is velocity of light, it will balance, okay, by taking into consideration medium in which it is moving. If it is going through longer distance, then it will manage its velocity in such a way that ultimately all light signals will take same time to reach output. So problem of dispersion, we are able to overcome in graded index. That's why graded index fibers are more beneficial index profile. A fiber which is referred as non-dispersive shifted fiber. So what is that particular fiber called as? So a standard single mode fiber having step index profile, it is called as non-dispersion shifted fiber, because here we are taking single mode. Single mode means where all light signals will move in single direction, so there won't be any problem of dispersion. And all these fibers, they'll have zero dispersion wavelength. What is dispersion? Broadening of pulses, where different light signals will take different times to reach output. That problem we are going to overcome in case of single mode fibers. And of course, here single wavelength transmission in O band. So they are referred as single wavelength transmission in O band. Then what are the performance characteristics of multi-mode graded index fibers? So if you take multi-mode graded index fibers, they use a constant grading factor in order to have better performance characteristic. And that based on the grading factor, what you will observe here is, of course, apart from having a good performance characteristic, they are going to have lower generation. Then coming to last definition, what is the bandwidth of multi-mode step index fibers? So if we take multi-mode step index fibers, they have bandwidth of 6 to 50 megahertz. And here, these fibers with this bandwidth they are best suitable for short haul, limited bandwidth and relatively low cost application. So I hope that by taking all these definitions, we are going to have better in understanding about lasers and fiber optics. So I'm going to end my session here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.